Okay, it's nice to be back. Now we are going to start with lecture one. In lecture one, I'm going to show you some equations and also trying to set the stage of what we are going to actually solve. We are not going to do too much density functional theory just yet, but I'm just going to explain what problem we are trying to solve. I will cut lecture one in two parts just to make it easier for viewing online. So the equation we're interested in is this one. This is the time-independent Schrödinger equation. I insist on operator. This is why the little hat on H means. So H is actually a complex object. It's not just a number. And we are trying to solve for that equation, which looks very much like an eigenvalue equation. We know that it's really what we need to solve. It's not an easy problem to solve. However, if we were able to solve it, we would have access to the wave function psi, which is given with all these parameters on this next slide. And so we have to understand that the wave function in quantum mechanics is really this complex function, which if you could solve for it, you would know essentially anything and everything you want to know about a system. So it's almost quasi-philosophical here, in the sense that can you ever know everything about a system? Well, today we can't. There are no systems that we can know everything about, but there are aspects that we can know about. And those aspects is really what we are trying to focus on. So the variables that we are working with are the variables that we have access to at this point. For example, the positions. So you have to realize that the wave function is an object that describes a system. So in this case, the wave function is a system of electrons, which are described by the position x1, x2, and so on, and of nuclei, I will sometimes call them ions, which are positioned at R1, R2, and so on, all the way to Rm. Now, what that wave function here does not include is the spin, for example, but it could. The spin could be another variable, which I didn't write explicitly, but it's another variable of the wave function. Now, this object is extremely complicated. I always like to ask when I give this lecture is students, and usually they know the answer, is that let's suppose I have 1 gram of matter, and 1 gram of matter is little matter when you look at the universe, right? And I ask, how many particles do you have in 1 gram of matter? And I talk about electrons really here. I'm not going into subatomic particle. And of course, we know that there is about 10 to the power 23, so about Avogadro number of electrons in about a gram of matter. I mean, give or take, right? 10 to the power 23. So this means that my n or m in this wave function here would take a value all the way up to 10 to the power 23. This is actually bigger than your mind can imagine. In fact, if you remember your days in high schools and you were looking at multivariable functions, you realize that when you had 2, 3, or 4 variables, it was already a formidable task to make sense of all the calculus and everything. Of course, as you moved on, you realize that you can do it, but nobody prepared you to look at 10 to the power 23 variable. Nobody is prepared to do that. And yet, that's exactly what the quantum mechanical problem is about. That's also why the classical approach to physics still has very bright days ahead, simply because we cannot solve everything quantum mechanically. However, there are conditions under which, especially in the low scale, the angstrom nanometer scale, where we need to use quantum mechanics. We will get to that. But what I want to impress upon you is the formidable task it is to solve the Schrödinger equation, so the time-independent Schrödinger equation I showed you on the previous slide. So what's nice about the wave function, though, expressed here in the representation of positions, as we know, this is an abstract object here in general, but here I represent it on the basis of the position of the electrons and the ions, is that the square modulus of that wave function gives you information about the density of electron at a given set of points. So that's basically giving you a probability or distribution, probability distribution. So this is what's useful about it. So if you were able to solve for this, you would know where all the electrons are, or at least the probability of finding them. And then as a result, you could find all the observable and other information you need. So this is something that's very important. Now, the wave function square is actually nice because it gives you access to a density, and this is something that we can visualize a bit better. Now, let's go to the fundamentals from quantum mechanics. We know that all the information is indeed contained in the system's wave function. We are here working on density functional theory as applied to materials, condensed matter physics, or even molecules. So we will be concerned here with electron and ion. One thing that we will realize is that we are going to separate, in fact, the problem of the electrons and the problem of the ions. I'm going to do that in a few minutes in this screencast in the Born-Oppenheimer approximation. And the ions will really be treated classically with the idea that they are going to generate an external potential. I'm going to insist a little bit on this notion of external potential in a few slides. And so the Born-Oppenheimer approximation, which I'm going to explain. Now, of course, I have to tell you a little bit about atomic units. Here, we are not going to be too concerned about the units. We are going to suppose that the charge of the electron is 1, the mass of the electron is 1, the Planck constant, the reduced one, so h bar over 2 pi, h over 2 pi, so h bar is 1, the Coulomb constant is 1. Okay, why do we do that? Well, we do that because we can always do that, and so we redefine units, which in this case are called atomic units, and that makes the equation simpler. We don't have to carry E, M, h bar, 1 over 4 pi epsilon 0. Frankly, and it almost pains me to say this, but you should not worry too much about this, because those things are not part of the intuition that we are talking about. Of course, they are part of being accurate, but the intuition I want to develop in this course for you to understand the result of the code is not related to the units we are using. What I mean by that is that since we have those software that works so well, let them figure out the units so long as we have an idea of what they should be. Now, there are tables of conversion for the different values, and this is an example probably obtained from Wikipedia. So I recommend that you are familiar with some of the orders of magnitude, of course. One thing that actually is useful when you translate atomic units into real life units is that physicists love EV, chemists, material scientists love kilocalorie per mole, and there is a one-to-one correspondence between them of about 23.06, which is actually interesting numbers now that I look at them, and they correspond to the connection between the two. One thing that's also useful to know is that KT, even though DFT is a zero temperature theory, KT, so Boltzmann constant time temperature, at room temperature is about 25 millieV. These are numbers, it's useful. Another useful notion is what's called the chemical accuracy. And so this is something that quantum chemists and physicists, computational physicists have been trying to solve, is that even though we are solving equations that are in principle exact, there's always somehow a limitation due to numerics and also a limitation about simply being able to do a calculation. And so that means that we do not have 100% accuracy. Just like experimentally, you never have 100% accuracy in your measurement. You always have a delta or statistical errors and stuff like that. So it's not, it exists, it's there. But so accuracy of perfect accuracy is not, there is no such a thing. However, we would love to have chemical accuracy. The chemical accuracy, which is about 1 kilocal per mole, would be an accuracy that if we can achieve that computationally, we would be able to, for example, design drugs or design different chemicals without the need of really testing experimentally if they're indeed correct. So if we were confident at 1 kilocal per mole, we would be able to do 100% screening using calculations. We are not there yet for the main part. However, methods like DFT, especially with the newest development, allow to get accuracy that are pretty close, actually not exactly close, but fairly close, and enough as a first screening step. So really, really accelerate the discovery of new materials or the understanding of existing one. Now, what are we solving in DFT, or in fact in this Schrödinger equation? So before we go there about what we are actually solving, it would be useful to look at the single electron Hamiltonian. The single electron Hamiltonian, this is the example here. The first part is the kinetic energy that we know. You will note here that h bar and m have actually been written explicitly. In atomic unit, we would drop those. So this is the kinetic energy, the first part. The second part is what's called the external potential. And by external potential is anything that's outside of the electron. So for example, if the electron is orbiting around the proton in a classical way of talking, the external potential would be the potential due to the proton. Okay, so this is really the Schrödinger equation of the electron in the hydrogen atom. It is not, I mean, to be really, really pedantic here, this is not the Hamiltonian of the hydrogen atom. It's the Hamiltonian of the electron in the hydrogen atom. I think this is actually interesting to know, because then at least you understand that the wave function refers to the probability amplitude of the electron, not of the whole system. This is a non-relativistic version of Schrödinger equation. There are ways to solve the relativistic version, which would be solving Dirac's equation, but we are not going to be too bothered by this. Now, the next slide is where people usually stop caring about doing science. Of course, not people watching this, but people who say, "Oh my gosh, these equations scare me. I don't want to do it." Well, it's just because notation. I mean, this is just a notation thing. It's actually not super complicated. Let me spend a minute to explain to you what we have on this slide here. The first line is just what I wrote a couple of slides ago, which is the time-independent Schrödinger equation. But now I put the variables, so the position of the electrons and the position of the ions, explicitly in the system, in the notation. Now, in the yellow box is really the important bit. This is the Hamiltonian operator. So it's an operator that corresponds to the energy terms in your system. Now let's look at each of those terms one by one, and you realize there's nothing to be scared about. In fact, this is the irony of the whole thing. You can easily describe each term in the operator. You can know exactly what they are. There's nothing mysterious. However, solving for them is next to impossible without clever ways, just such as density function theory. So the first term is the kinetic energy of the electron. So you sum over all the electron from 1 to n. The next, so it's atomic unit, there is no m, there is no h bar, there is no nothing. The second term is the kinetic energy of the ions. So now, of course, there is a mass, because an ion has a mass that's larger than the mass of the electron. So therefore, you have a mass Ma there. Ma is essentially the ratio between the mass of the ion and the mass of the electron in those units. Okay. Now the next, so these are two kinetic energy. The next term is interesting. The next term, if Za is the charge of the ion A, then and Ria is the distance between electron I and ion A. This is simply an attractive force, an attractive potential. Sorry, not a force, attractive potential, which is which correspond to the electrostatic interaction between an electron and a positive ion. It is attractive, and you can know that by looking at the negative sign. So That means the larger that term, the more negative and therefore the more stabilizing it will be. Now the next term, which actually looks the simplest in the notation, is simply a sum over all the electrons pairs. And this is actually positive. This is a repulsion between electrons, right? So you sum over that. Now, there is an important aspect that I want to insist a little bit is on the index J. So of course we sum over all the electrons I from 1 to n, but we only sum over the J that are larger than I. Why do we do that? First of all, we do that so we do not double count, because the interaction between I and J is the same as the interaction between J and I. If we were counting them twice, we would be double counting. So that piece is easy. Now, we cannot, and this is something sometimes students should take a minute to think because it turns out to be fundamental, you cannot also consider J equal I. Because if you consider J equal I, that means that the electrons will be interacting with itself. I'm sorry, but electrons do not interact with themselves, not in this way. And there would be two consequences, of course. If they interacted with each other, Rj would be 0, so it would be a fairly large number, very, very large number, in fact. And then of course you would add interaction that do not exist. Now it may seem obvious to you when I say this. It turns out that this is called the self-interaction error or self-interaction correction, so that density functional theory has to deal with, because you will understand why this becomes an issue in density functional theory. Okay, and finally the last term is also a repulsive term. Same thing here, where we have between the ion A and ion B. And again, the sum is over B over A. So this is the Hamiltonian. This is your entire Hamiltonian. Here, I'm not going to insist too much on the spin degrees of freedom, even though DFT can handle that as well. But just to make it simple, this is the Hamiltonian there. There's nothing crazy. It's kinetic energy and just the electrostatic part. Okay? Now, this is really what we have to solve. This is already very hard to solve because we have many electrons, we have many ions. So the first thing we are going to do is to try to solve this, to simplify this a little bit, and it's going to be called the Born-Oppenheimer approximation. Now, I would like you to think a little bit about another kind of a metaphor here. Imagine that you have all these electrons moving around ions. You have to realize the ions, a proton is about 2,000 times heavier than an electron. So a proton is just is a very small nucleus. So most nuclei will be much bigger than that. So in other words, imagine the best way to think about that is that you have a bunch of elephants on the plane, and there are little birds flying around them, very light birds flying around them. They are being attracted by the birds are attracted by the elephant because the elephants have some insect on them, and so but they don't want to also they don't collide with them. So you can imagine this swirling and moving birds around the elephant. The elephants are very slow. They are so much bigger than the birds that are moving really slowly, and the birds go all over the place. So basically, from the perspective of the birds, the elephant moves so fast that it's very easy to predict the trajectory and so on. They don't have to worry too much. They basically can use a snapshot of the position of the elephant to describe where the birds are going to move next. So this is exactly what the Born-Oppenheimer approximation is. The Born-Oppenheimer approximation suggests to separate the motion of to decouple essentially the motion of the birds from the motion of the elephant. So that comes from the fact that we can treat the interaction between the elephants. So in this case, this is the electrostatic repulsion that we have here between the ions. This is between the elephant. Can treat this classically. And on top of that, we can basically get rid of the kinetic energy operator in the Hamiltonian because of the mass of the ions is so large. I will notice that do not confuse this for the classical treatment of motion of the ions like we would do in molecular dynamics. That molecular dynamics will indeed be classical in that perspective. But in that case, when we do the molecular dynamics, which we treat classically, we do not worry. We do worry about the kinetic energy of the elephant. But in terms of the operator, quantum mechanical operator, we can drop that term in the sense that it does not contribute to the total energy of the system. I would like to insist again that now this term, which is the attractive term between the bird and the ion, so between the electron and the ions, which is an attractive term, as I said, because it's electrostatic, that term is now going to be considered external potential. External because it's external to the electrons. It's a term that actually come up because of the presence of the ions, seen as basically in a frozen snapshot, just like the bird moving into the elephant, which are in their time scale. So the time scale for birds to move a certain distance, the elephant has not moved. That's basically what this is. Okay, this is called the external potential. I will actually talk about that a bit more later. Now, when we come to total energy now, we see the total energy can now be the electronic part plus the nuclear part. And the nuclear part is obtained by the equation I gave you before. And we basically, in this particular description, we ignore the kinetic energy of the ions, as I said, because of the mass is so large. And the electronic energy can be obtained now by another Schrödinger equation, another time-independent Schrödinger equation now that only looks at the electronic degrees of freedom. So I'm going to continue this discussion in the next screencast, which will be the second part of this lecture. Thank you.